Okay, now we're going to learn the chapter 20, which is the last chapter for this course. And we're going to learn the second law of thermodynamics in this class. Okay, so first of all, in this chapter, it's mainly conceptual chapter. So you will learn the concept of the second law of thermodynamics. There are relatively small amount of calculations, and the equations you'll learn in this chapter will be relatively easy. So it's not a big amount of calculation. So the main goal for this chapter is the concept of the second law of thermodynamics and some other concepts which are related to the second law of thermodynamics. Okay, so in this chapter, we're going to learn the difference between reversible and irreversible process. And then we're going to learn the physics of internal combustion engine. And then we're going to learn how refrigerators and heat engines are related and how to analyze the performance of a refrigerator. And then we're going to learn the second law of the thermodynamics and sets limits on the efficiency of engines and the performance of refrigerators. And at the end, we're going to learn what is entropy and how to use entropy to analyze thermodynamic process. Okay, so before this chapter, let's ask several questions. So why does heat flow from hot material to cooler material, like it flows from lava to cooler water? And can it flow to the other way, for example, from some cold object to hot object? Is that possible? Third question, is it easy to convert um, mechanical energy completely into heat? But if you want to convert the heat into mechanical energy completely, that's very difficult, or it's impossible. Why? Last, we need to use the second law of thermodynamics and the concept of entropy to answer all the questions. Now let's start. So first of all, the directions of thermodynamic processes. The direction of reversible process can be reversed by an infinitely small change in its conditions. Now let's see some irreversible process here. So here we show a system which is a metal box and a piece of ice. Let's say at the beginning, let me change the pointer of the pen. At the beginning, the temperature of the metal box is 70 degrees, and for the ice, it's 0 degree. And a block of ice will be melt irreversibly when we place it in this box. This is 70, this is 0, so the heat will flow from the box to the ice. And at the end, you will see the liquid water might be melted, and the temperature of the liquid water finally becomes 40 degrees. And the metal box is also 40 degrees. So the heat flows from the box into the ice and water, and it never reverses. This is irreversible process. Now let's see another process, which is reversible process. Now if we put the ice and the box, let's put the ice into the box. The ice temperature is 0 and the box temperature is also 0. And this block of ice can be melted reversibly if we put it in this melted box and we infinitesimally infinitesimally raising or lowering the temperature of the box. So by infinitesimally raising the temperature of the box, you can make the ice to be water. And if you do uh, if you, let's say, decrease the temperature infinitesimally, then you can uh, make the ice, you can make the water into ice again. So by using this infinitesimally raising or lowering the temperature of the box, you can make the heat flow into the ice or melt it, or make the heat flow out of the water to refreeze it. So this is a reversibly process. So the difference between the reversibly and irreversibly um, processes in this ice box situation is, so here at the beginning the temperature of the metal box and the ice are the same, and you infinitely um, you infinitesimally raising or lowering the temperature. However, in a irreversibly process, the metal box and the ice at the beginning has a great temperature difference. So at the end, they will have the same temperature, but it doesn't automatically um, go to the um, reversible way. For example, the water will never um, give up his heat, or the heat never flows from the water to the box automatically, which makes the 40-degree water into 0-degree ice and makes the metal box from 40 degree to 70 degree. So the heat doesn't flow from low temperature to high temperature. That's the difference between reversibly and irreversibly processes. Now let's see another concept, which is heat engine. A heat engine is any device that partly transforms heat into work or mechanical energy. All the motorized vehicles other than purely electric vehicles use a heat engine for propulsion. For example, most of our cars, they're using the heat engine for the propulsion. And hybrid vehicles use their internal combustion engine or heat engine to help to charge the batteries for the electric motor. So it's a mixture. So the hybrid vehicle, as their names, they're kind of mixture of electric engine and heat engine. Now let's see what's the workflow for heat engine. Here is a schematic picture of heat engine. A simple heat engine operates on a cyclic process during which they absorb heat HQ from a hot reservoir and discard some heat QC to a cold reservoir. Let's see, this is a hot reservoir, and here it's a cold reservoir. So for a heat engine, it will um, absorb some heat QH to the engine, and some of the heat uh, will flow to the cold reservoir, which is um, QC. And the difference between QH and QC, so um, so we have learned the energy and work as a pre-lecture. If you remember that lecture before the thermal and fluid. So in the work and um, energy lecture, we have learned So for the whole system, if we consider this as a whole system, um, the change of the heat and the change of the work should be zero. So the change of the heat must be converted into the work. So you have some heat flows out from the hot reservoir HQ, and some heat has been observed by the cold reservoir, which is HC. So the difference between QH and QC should be the work that is done from the system. So this is the work has done from the engine. So from this schematic energy flow diagram, we can see there's some QH flows out from the hot reservoir and some QC has been observed from to this cold reservoir, and the difference between QH and QC is the work done by the engine. And of course, W equals to QH plus QC. And QH is positive, QC is negative. So we can define the efficiency of a heat engine. The thermal efficiency E of a heat engine is a fraction of QH that is converted to work. So E equals to W over QH. So this is W, this is your QH. And W over QH equals to, because W equals to, do you remember? QH plus QC. So W equals to QH plus QC, so it equals to QH plus QC over QH, which is 1 plus QC over QH. Remember, QH is positive, QC is negative, so it also equals to 1 subtracted by the absolute value of QC over QH. So E, the efficiency, is what you get divided by or what you pay for. This is always less than unity, and all too familiar experience. Okay, now let's see the working process of internal combustion engine, which is similar to all the other heat engines. This is the cycle of the internal combustion engine. Let's see, at the beginning of the cycle, it's intake stroke. You see, this valve is open, so the air has been um, intake has been intaken to the cylinder. So the piston moves down, causing a partial vacuum in cylinder. The gasoline and air mixture entered into this cylinder, and then while um, while it's moving to the second stage, which is a compression stroke, so both valves are closed. So the mixture is compressed by this piston when the piston is moving up. And then when the air is compressed, the temperature is getting higher, the pressure is getting bigger, the volume is getting smaller, and at this moment you can spark the fire, which ignite the mixture of the gas, and then it burns the mixture of the gasoline, and the air will burn. So the temperature is getting even higher, and then because the temperature is getting higher, so the pressure um, is getting higher, it will push the piston down, so the pressure is getting lower in the fourth stage, which is power stroke. So the volume is getting bigger, the pressure is getting lower because the volume is getting bigger. And then um, while the piston is moving up, um, the exhaust valve opens. So the exhaust so the valve, the other valve or the exhaust valve is open, so the air will be expelled um, from the cylinder. And then this valve, this exhaust valve will be closed again. And then this intake valve will open and the piston will move down in next stage, which is exactly the stage one. So that's a whole cycle of the internal combustion engine working. So if we draw a PV diagram of the entire process in this internal combustion engines, you can see the curve is like that. For example, at stage one, um, when this is compression stroke, okay, so actually this is, let's see, from A to B, this is gasoline air mixture, which is compressed adiabatically and then ignited. This is the process of stage 2 and 3. First, the volume is getting lower and the pressure is getting higher. So in this stage, the volume is smaller because the piston is moving up and the pressure is getting higher. And then it ignites the mixture of the air. So the heat is generated, then the temperature is raising, then the entire PV diagram is moving in this direction. So this is the heating at constant volume. So you can go through the entire process according to the descriptions. It explains what happens in each state. And you will see in the entire curve, the dark area is work has been done to from the engine. Okay, so that's another cycle, which is for diesel cycle. So it's slightly different from the gasoline cycle. So you can read it by yourself. Now let's see another concept, which is refrigerator. So refrigerator works in the opposite way from engine. So for refrigerator, it takes heat from a cold place and gives it to a warmer place. And input of mechanical work is required to do this. For example, in a cold place, it takes some heat from the cold place, and then this heat will be transferred to a hotter place. When doing this, you need some work. So that's the work. So a refrigerator is essentially a heat engine operating in reverse. So here is an energy flow diagram for refrigerator. And for the efficiency of refrigerator, we use QC over W. We call this ratio of the coefficient of performance, K, QC over W, and W is QH subtracted by QC. So here is a diagram of what is a cycle of a refrigerator. So you can read it by yourself. But essentially, what a refrigerator do is it has a cooler side and hotter side. For example, in your refrigerator, from the cooler side, it has some heat flows from the cooler side to the hotter side. And you also need some work to, let's say, you need some work um, to this entire process so that the heat can be taken from the cooler side to the hotter side. And the second law of thermodynamics can be stated in several ways. First, it's impossible for any system to undergo a process in which it absorbs heat from a reservoir at a single temperature and converts the heat completely into mechanical work, with the system ending in the same states in which it begins. Or simply, it doesn't happen if you only has a hot reservoir and you convert some uh, heat into work, it never happened. So when you want to convert some heat into work, it always uh, wasted some heat from QH to QC, and meanwhile you can do some work. So you cannot 100% or perfectly convert the heat into work. And we call this engine statement of the second law. Another way to describe the second law of thermodynamics is it's impossible for any process to have its sole result the transfer of heat from cooler to hotter body. For example, you have a hot reservoir and you also have a cooler reservoir. It never happens that the heat can flow from the cool reservoir to hot reservoir. In order to transfer some heat from cooler to hotter place, you always need to do some work. So this is the second statement. We call this refrigerator statement of the second law. Okay, and the two statements actually um, are uh, kind of similar or same because um, because if a workless refrigerator were possible, or the refrigerator statement is possible, if this is possible, then the first statement is also possible. Let's see. If it's possible that the heat can be transferred from cold place to a hot reservoir without any work done, then you can combine this process with another engine. Then you will see this engine, by combining these two processes, you will see this engine is doing some work without transfer any heat to the cold reservoir, which is 100% efficient engine. This is If this is impossible, this is also impossible. And the reverse is the same. It is also true. If um, if 100% efficient engine um, is possible, for example, the Q could be transferred completely into work. Then you can use this work to in a refrigerator, um, which can be transferred QC into QH plus the work. Then by combining this 100% efficient engine plus the refrigerator, what you get? You get something which is transfer some heat from cold place to hot place. So if this is possible, then that is possible. However, this is impossible. So this is also impossible. Okay, Carnot cycle. It's another different type of engine. You can read it by yourself. It's not. It won't be in our. The calculations of Carnot engine will not be in our exam. However, in our exam, we could have some conceptual question about Carnot engine. So please read it and understand by yourself. Engine efficiency. To maximize the efficiency of a real engine, the designer must make the intake temperature as high as possible and the exhaust temperature (Tc) to be as low as possible. So for this reason, the temperature inside a jet engine are made as high as possible. Exotic ceramic materials are used that can withstand temperatures in uh, excess of 1,000 temperatures without melting or becoming soft. So this is Carnot refrigerator. Now let's see the Carnot cycle and the second law. So no engine can be more efficient than a Carnot engine operating between the same two temperatures. Okay, please try to understand by yourself. I have helped you to understand the previous two impossible cases. For this case, in this slides, please try to read the textbook and the slides and help yourself to understand it. Now, let's introduce a very important concept in physics, which is entropy. So, entropy actually is a quantitative measurement of disorder, or entropy is disorder, but it's more quantitatively concept. So many processes proceed naturally in the direction of increasing randomness. For example, when you add heat to a body, then the body or object um, will get the heat, and the heat increases average molecule speed, and the molecules in the object becomes more random. The explosion of firecracker here shows increase its disorder and entropy. So before the explosion, the firecrackers they are more ordered. So they have individual firecrackers organized very well, but after the explosion, you will see it's messy. So everything's disordered and random. So that means the entropy is increasing. And we define entropy um, of a system to be S, and S ds equals to dq and dt, which is infinitely small reversible process. The total entropy change over any reversible process could be described by this number. The delta, or the change of entropy, equals to dq over t, and you can take the integral from state 1 to state 2. Then that's the entropy change from state 1 to state 2. The total entropy change in one cycle of any Carnot engine is zero. This result can be generalized as shown. The total entropy change during any reversible cyclic process is zero. And the second law of thermodynamics can be stated in terms of entropy. So this is the third statement of the same law, which is the second law of thermodynamics. No process is possible in which the total entropy decreases when all systems taking part in process are included. So for example, if you drop ink into water, then the water and the ink will eventually get mixed, and it will mix better and better, and at the end they're completely mixed together. This is entropy increasing process, because in this case at the end the entropy uh, is the highest, the disorder is highest. Suppose okay, so why? So it could be explained by microscopic interpretation of the entropy. So suppose you have n identical coins on the floor. Then the most probable outcome of tossing n coins is that half of them are heads and half are tails, because when the heads and half um, when the heads and tails are half and half, then this microscopic state has the greatest number of corresponding microscopic states. If we let W represents the number of possible microscopic states for a given microscopic state, then the entropy of a macroscopic state can be shown by this equation: S equals to K ln W. Here K is Boltzmann constant, W is number of microscopic states. And in the free expansion of n molecules, in which the volume doubles, the number of possible microscopic states increase by a factor of 2n. For example, if you have some gases occupy the volume V, then the microscopic state is W1. And if you kind of open a door or a hole between the upper and level space, then eventually the molecules will be mixed into the entire 2V volume, because in this 2V volume, the number of microscopic states is greater, which is W2. It equals to 2 to the power n times W1. So the disorder increased, the entropy increased. So in nature, the process is always prefer going in the direction of increasing the entropy or increasing the disorder. So that's the concept of entropy. And that's all for this class. And also this is all for this course. So please read the textbook a couple of times to understand the concepts. In this chapter, you met several completely new concepts, like entropy, like the engine, actually the mechanism of the heat engine and the refrigerator. They're all new concepts, so please read carefully the textbook and do the homework on time, and try to understand everything and do some calculations in this chapter. So that's all of our chapters. So in next week, I'll release some other video to help you to understand the energy and the work. So if you remember, we have this chapter of energy and the work as our pre-knowledge before we officially learn thermal and fluid. So I will make a video for the work and energy and release the video in next week. Okay, so that's all for today. So I will see you in next week.